Hello everyone. So in this part, we'll be learning about the particles exhibit wave behavior with a wavelength that depends on the momentum of the particle. So this de Broglie's wavelength can be determined by the formula that is lambda, which is h Planck's constant, divided by the momentum of the particle. Okay, let's compare light and particle. Light are basically bundles of energy. So light has energy, and the energy of a light photon is proportional to the frequency, hf. H is your Planck's constant, and f is the frequency of the light. Or is also same as hc over lambda. So energy of a photon is inversely proportional to the wavelength. On the other hand, for a particle will have kinetic energy, and the kinetic energy of a particle will be half mv squared. So we don't say a photon has kinetic energy because a photon is energy. Okay, for momentum, right? A photon is a particle, so it will have momentum as well. And the momentum of a photon is h over lambda. So unlike momentum of particles, which is given as mv, a photon do not have mass. So therefore, we don't write this m times c, right? So momentum is actually h over lambda. So lambda will be the wavelength of the photon. The wavelength of a photon is c over frequency. The higher the frequency, the smaller the wavelength. So on the other hand, a particle can also show wavelength behavior. So de Broglie said that the wavelength of a photon, or the de Broglie's wavelength, is inversely proportional to the momentum. So momentum is basically mv, or basically 2 square root of 2 mass kinetic energy. So how we derive this? How is this equivalent to momentum? Okay, we know kinetic energy is equal to half mv squared. So if we multiply m on both sides of the equation, what we get will be mass kinetic energy equals to m squared v squared. So if we multiply 2 on both sides of the equation, we get 2 mass kinetic energy equals to m squared v squared, which is the same as momentum squared. So in other words, momentum will be square root of 2 mass kinetic energy. Right? So this here is momentum expressed in terms of kinetic energy. This is momentum expressed in terms of velocity. So which formula that you use depends on what's given in the question. If you want to represent momentum, if the question gives you kinetic energy, then we use this to find the momentum. If the question just gives you the velocity of the particle, then we should use this formula to find the momentum of the particle. Okay, so let's try this question, pause this video, and then resume playing once you are ready. Okay, in this question, as you calculate the de Broglie's wavelength of the following: a 125-gram mass that's moving at 100 kilometers an hour, and a photoelectron with a stopping potential of 9 volts. Okay, let's solve for the first one. So you want to find the de Broglie's wavelength. First of all, we have to convert kilometers an hour to meters per second. So we need to change everything to mks, meter, kilogram, seconds. So 100 kilometers per hour, we times the conversion factor. 1000 meters is 1 kilometer. So kilometer and kilometer cancels out. Then we times the conversion factor. 1 hour is 3600 seconds. So hour and hour cancels out. So this will give us 27.8 meters per second. The same case goes for this, right? 125 grams changes to kilogram. So once we have done that, then ready to find de Broglie's wavelength. So de Broglie's wavelength will be Planck's constant divided by mass times velocity. So this will give us a de Broglie's wavelength of 1.91 times 10⁻34 meters. Okay, let's do the same for a photoelectron with a stopping potential of 9 volts. So what do you understand about stopping potential? So if the electron has a stopping potential of 9 volts, it means that the maximum kinetic energy of the electron is 9 electron volts. So let's find the de Broglie's wavelength, which is h divided by square root of 2 mass kinetic energy. So substituting kinetic energy as 9 electron volts, only thing will be 9 electron volts is not your SI units of energy. We have to convert 9 electron volts to joules. So you have to multiply by the charge of 1 electron. So Planck's constant divided by 2 times mass of electron times its kinetic energy, take the square root of that. So this will give us a de Broglie wavelength of 4.1 times 10⁻10 meters. Okay, remember just now the formula, right? When we want to find de Broglie's wavelength, we either use this momentum expressed in terms of kinetic energy, or we use momentum expressed in terms of velocity. So it all depends on what is given in the question. So since this question gives you velocity, how fast it's moving, then we use mv. In part B, right, they give you in terms of energy. So it's best when you express momentum in terms of kinetic energy, rather than from kinetic energy, we find how fast the particle is moving. And once we find how fast the particle is moving, then we use mv to find the momentum. So try to minimize the amount of steps in your exam, right? So we use momentum expressed in terms of kinetic energy. Okay, think of the difference in the answer. So for a normal, let's say a ball, right, of 125 grams, it will have a de Broglie's wavelength of 1.91 times 10⁻34 meters. On the other hand, electron will have a de Broglie's wavelength of 4.1 times 10⁻10 meters. Okay, let's go back to Young's subatomic experiment. So Young's subatomic experiment, you had a photon that struck a single slit, and when the photon passed through the single slit, it diffracted. Right? So the condition for us to say diffraction would be when the slit size is larger but comparable to lambda. So in the case for visible light, lambda is in order of times 10⁻7 meters. So the d, right, that we use for Young's subatomic is in the order of times 10⁻6 to times 10⁻5 meters. So it's larger, right? But it's comparable to lambda. So when I say larger, it cannot be like, say this is 1 centimeter, but lambda is times 10⁻7 meters, then it's not going to work. You don't see diffraction. So for diffraction to take place, the slit separation must be comparable but larger to the wavelength of the source that we are considering. So similarly, for Young's subatomic, there are two slits where the slit separation is again comparable to lambda. Okay, in the case of a baseball, let's say this is a baseball. For us to see diffraction of a baseball, we need to have the baseball pass through a slit. So the size of the slit must be greater or equal, comparable to lambda. What was the lambda of a baseball? The lambda of a baseball is in the order of times 10⁻34 meters. So in other words, I have to pass this baseball through a slit that's in the order of times 10⁻33 meters or times 10⁻32 meters. It's impossible to do that because your interatomic spacing is in the order of times 10⁻15 meters. So it's impossible to pass a baseball through atoms that is separated by times 10⁻50 meters. What more if you want to pass it through something that is in the order of times 10⁻32 meters. So in other words, right, although de Broglie tells us that this baseball will have a wavelength, but it's impossible to see the wavelength of a baseball. So the main property of a baseball will be it behaves like a particle rather than a wave. On the other hand, electrons, right, has a wavelength of times 10 minus 10 meters. You see 4.1 times 10 negative 10. So it's much larger as compared to the wavelength of a baseball. So it's possible to see the wavelength behavior of electrons, because it is possible for us to pass electron through slit separation in the order of times 10 negative 9 meters. Right? So for electrons, right, it's possible to see the wavelength behavior of electrons. So we not see diffraction of a baseball. Okay, let's try this example again. So pause this video and resume once you are ready. Okay, in this question, they ask you to calculate what is the energy, right? The energy of electron and photon. Both of them have 10 electron volts of energy. So if the electron has 10 electron volts of energy, what's the wavelength? And if a photon has 10 electron volts of energy, what's the wavelength of the photon? So for electron, right, since we are given energy, then we use the de Broglie's wavelength, where momentum is expressed in terms of kinetic energy. So from the law of conservation of energy, kinetic energy is 10 electron volts, right? So 10 electron volts is not your SI units of energy. So we have to find what's your energy in terms of joules, right? So what we do is we just times 10 with the charge of one electron. So to find the de Broglie's wavelength, we express momentum in terms of kinetic energy. So we substitute values, 2 times mass of electron times the energy of 10 electron volts. Now that's represented in terms of joules. This is your Planck's constant. So the de Broglie wavelength will be 3.88 times 10 negative 10 meters. Okay, what's the wavelength of a photon? So wavelength of photon, E equals to h over lambda. Take note the formula that we use is totally different, right? So whenever we deal with normal particles like electrons, protons, and so on, then they have a mass. But photons are particles of energy. They don't have mass. So the formula that we use for photons will be h over lambda. So we know h, we know c, we know energy. Again, energy has to be converted to joules. So we can find what is lambda. So the lambda will be 1.24 times 10 negative 7 meters. But the wavelength of an electron that has the same energy of 10 electron volts is 3.88 times 10 negative 10 meters. So most common confusion is students, right? They tend to use this formula for electrons, or they use this formula for photons. So whenever there's a C there, then we use it for photons. Photons travel at the speed of light, but they don't have mass. So any other particles have mass. So we use the formula that describes the mass of the particle. We don't use this formula anymore. Let's look about de Broglie's hypothesis. So de Broglie's hypothesis is that all particles will show wavelength behavior. So therefore, they must have a wavelength. And this is known as your de Broglie's wavelength. Okay, next, the wave behavior of particles can be demonstrated using Young's double slit experiment and Davison-Germer's experiment. So Young's double slit is 2 slits. Davison-Germer experiment is basically a diffraction grating. Okay, to see the interference that's similar to Young's double slit, I have an electron gun that passes through 2 slits, right? And I have a photographic film. So when the electron passes through the slits, right, the electron will strike the photographic film. And when it strikes the photographic film, it causes a spot to be seen. So as more and more electrons comes in, right, the image will gradually build up. And what you eventually see will be regions of constructive and destructive interference. So this is constructive, here is destructive, followed by constructive, destructive, constructive, destructive. So this diffraction of electron demonstrates that electrons are actually a wave. Because the only way to explain why interference happens is that it has wave-like behavior. Because a particle do not interfere. If I have a pen, all right, if I bring the two pens together, the pen do not suddenly disappear. All right? Or if I bring two pens together, suddenly I get a much larger pen. So this demonstrates that electrons, traditionally known as particle, demonstrate wave-like behavior. Okay, Davidson-Kermer experiment. So before I explain about Davidson-Kermer experiment, I need to explain about two kinds of diffraction grating. One is known as the transmission diffraction grating, like what we learned already in subtopic 3.1 is a transmission diffraction grating. The transmission diffraction grating is you have a light source, like a laser light source, that strikes a diffraction grating, and the interference pattern that you see lies on the opposite side. Right? So this is your light source, and this is your interference pattern, central maximum, first order maximum, and so on. The next type of diffraction grating is known as a reflective diffraction grating. So a reflective diffraction grating will be your light source is on the left-hand side. When it strikes the diffraction grating, the interference pattern that you see lies on the same side as the light source. So both of them lies on the left-hand side of the diffraction grating. So typically, right, we don't shine the laser beam perpendicular to the diffraction grating in the case of a reflective diffraction grating, because it's hard to measure this beam, right, the central maximum. So what we do is we normally shine it at an angle. So when we strike at an angle, this is the reflected beam, which is also the central order maximum. So to see the first order maximum, then you see the beam branching out. So this is my first order maximum, this is my central maximum, and this is my first order maximum. So in this case, if I want to measure angle theta, this is my angle theta between first order maximum to central maximum. Just like for a transmission diffraction grating, central maximum, first order maximum. So whether is it a transmission diffraction grating or a reflective diffraction grating, the formula that we use will still be the same d sine theta equals to m lambda. Okay, Davidson-Kermer experiment is basically a reflective diffraction grating. So they use a low energy beam electron, strike a nickel crystal, and they move a detector around to basically study the scattering of electrons. So Davidson-Kermer, right, actually set up this experiment to study the scattering of low energy electrons. So scattering is basically considering that the electrons are particles. But to their surprise, right, when they did the experiment, they found that they observed a certain maximum. That means the electrons appears to be collecting at a certain angle where it appears to be maximum. So this here is actually demonstrating constructive interference. So when they move the detector around, they found that at an angle of 50 degrees, I detected a certain maximum. So this is where you get constructive interference. So now we can explain what happened. Because when the low energy electron strikes the crystal surface, so the crystals, right? Like when you learn in chemistry, what's so special about crystals are that the atomic arrangement of crystals are in a very systematic order. That means the distance between adjacent atoms are basically acting like a natural diffraction grating. So when the electron, which is a wave, strikes the atomic spacing, which acts now as a natural diffraction grating, the electron diffracted. So when the electron diffracted, it interfered and caused a certain constructive interference at a certain angle theta. So this was what Davidson-Kermer experiment demonstrates, right? Okay, let's try this question. Watch this video. Okay, in this question, in a Davidson-Kermer experiment, an electron beam was accelerated through a 160.4 volts potential. on the crystal surface or nickel crystal. The interatomic spacing of the nickel crystal atoms are 0.215 nanometer. The question is determine the de Broglie's wavelength and the angle in which the second order maximum would be observed. So this is a diffraction grating. So diffraction grating, right? We can use d sin theta equals to m lambda. But first of all, let's find what is lambda. So using momentum expressed in terms of kinetic energy, because we are given the accelerating potential. So in other words, electron will have 160.4 electron volts of kinetic energy. So kinetic energy, we use this formula. So H, this is mass of electron. This is the energy of electron in terms of joules, right? So we find the wavelength will be 9.69 times 10 negative 11 meters. So this is the de Broglie's wavelength. So for B, right, the angle in which the second order maximum will be observed. So in this case, diffraction grating, we use this formula d sin theta equals to m lambda. So second order would be, that means m must be equals to 2. So we want to find sin theta for the second order. We can use this formula 2 times lambda, the lambda of the electron, which is this 2.69 times 10 minus 11 meter, divided by interatomic spacing. This is your d. So from here we can find the angle will be 60.41 degrees. Okay, let's try this example. Okay, so in this question, the beam of electron with de Broglie's wavelength of 1.54 times 10 negative 10 meters is directed onto some crystal that makes a glancing angle of 15.9 degrees. Right? So the reason why you strike it at an angle to the diffraction grating is so that we can measure the central maximum. Okay. So A, find the speed of the electron. Okay, if we are given de Broglie's wavelength, find the speed. That means we can use the formula momentum expressed in terms of velocity. So you're given de Broglie's wavelength, find v. So in this case, we can find v by equating this. So v will be 4.73 times 10 to the power 6 meters per second. Okay, v was the potential required to accelerate electrons to this speed. So what's the accelerating potential? So from the law of conservation of energy, the work done on the electron will be equals to the kinetic energy. So we know how fast the electron is moving, so therefore we know its kinetic energy. So from here we can find the accelerating potential, that is 1 divided by q times its kinetic energy. So substituting what we know, mass times v squared divided by 2 times 1.6 times 10 negative 19, right? The charge of electron times 2, right? From here, we can find the exciting potential to be 63.7 volts. And finally, what's the interatomic spacing? So we use the diffraction formula d sin theta equals to m lambda. The question is, what is d? So d is actually m lambda divided by sin theta. So m will be first order, theta will be 15.9, and we know lambda. This is de Broglie's wavelength. So from here we can find the interatomic spacing to be 5.62 times 10 negative 10 meters.